I'm a director of the observatory, and of course, all directors like to talk and to speak. So this is the second talk is due to my colleagues from China, which could not get the visa here, so therefore I have this possibility. So I will give a short talk about the Soviet Bolshoi. Bolshoi, you know this Russian word? It's Bolshoi, it's big, large. Everything is big in Russia. Territory, telescope, museums, ballet, Russian theaters, etc. So, and also a second part about how we are doing spectral interferometry with using our telescope. It moves slowly. Sorry. There's a big delay because of some reasons. So this is a map of former Soviet Union. It does not exist, unfortunately, anymore. Or fortunately, who knows? So the idea of building a very large telescope in Soviet Union was developed immediately after the Second World War, when Americans built the famous Hale telescope, 5-meter telescope. We measure every distances in meters. Please fix it, not in inches or etc. So in any case, the idea was to build the telescope which will be larger than the American telescope. We decided, not me, but astronomers decided to build a telescope with a mirror of the size of 6 meters. And of course, there were many expeditions where to put this instrument, and we had, at that time, Soviet Union had very good sites here on the territory of former Soviet republics, Tajikistan, Uzbekistan, in the mountains close to Pamir Mountains. And it was good seeing high altitudes, peaks, similar to Chilean mountains. But the leaders of Soviet Union, the leader was Kosygin, and this guy who is on this picture, the president of Academy of Science, Keldysh academician, they decided to build it on the territory of Russian Federation, not in these republics in Asia. And this was a very clever decision because these republics are lost and that we could lose the observatory at that time. So unfortunately, despite the huge territory of Russia today, forget about the southern part, it belongs now to independent countries. On this huge territory, which is 1/6 part of the world, there is no good site for doing astronomy. And they decided to build a telescope here in Caucasian mountains, somewhere closer to the Black Sea. So I live here. This is our observatory, somewhere here, Caucasian mountains. It's not a very good site because of the weather, because we are close to the Black Sea, and and therefore the humid air comes from the Mediterranean Sea, and we have half of the nights are cloudy, so we do not observe. So this is a building of the telescope, old-fashioned dome, old-fashioned classical dome, 53 meters high. I don't know how many in inches, so don't ask me. And the telescope is beautiful. It's very good, nice instrument. The mirror is here. This is the first large azimuthal telescope in the world. Of course, the azimuthal mounting was known before, but the idea to build a huge telescope using the azimuthal mounting was for the first time realized here, this telescope. And of course, the problem was at that time, because this was the beginning of 70s, the end of 60s, there were no computers for these goals, how to drive the telescope, but special computers were designed and built by the Soviet Union to control the instrument. Of course, this we keep it as a museum now because we control the telescope using ordinary PCs, but at that time it was a big problem. So the instrument has a focal distance 24 meters from the surface of the mirror to the prime focus cage here. It has two Nesmiths, we call it Nesmith, but Nesmith 4C here. And the whole weight of the instrument is about 800 tons because the drives are below. It's very heavy, but very stable, very good instrument. The focal ratio is f/4. So the distance from the floor here to the top of the dome is, as I remember, 35 meters. So we have many different instruments installed the telescope, including a small spectral interferometer which is installed here. But the telescope is now completely remote control, so there are no astronomers. When I was younger, the first speckle observations were made from the prime focus cage, and astronomers had to sit inside of the cage. And Russia is much colder than here, typically. Again, I cannot transfer this to Fahrenheit, or Fahrenheit, how you call it. In Celsius, we have, when it is minus 20 outside, so it's minus 20 in the cage. So it's very cold to sit all night long. Night starts at 5 in the evening and ends 7 in the morning. So 14 hours for me, because I was small weight, I'm still. And they liked very much to keep me inside of this cage. And no toilet, nothing. There's no restrooms in the cage, so it was a life. So, and in addition to the telescope, which is here, we have a village. For almost 1,000 people live there, but astronomers only 100. All others are not connected with astronomy anymore. Beautiful place, very nice, but colder than here. And the telescope is equipped with modern detectors. I would just example infrared detector. And in the past, this is taken from ESO homepage. In the past, the telescope was large, but today, this is Northern Hemisphere. Our SRO, Special Astrophysical Telescope, is here. So these are the mirrors of the instruments today. This is a mean number of clear hours. Maybe I can omit this, but these are months. And you see the typical value is about 150 hours per month. So it means about half of the night is clear. But also we found that the mirror, which is made practically from ordinary glass, like a window glass, because at that time, in the beginning of the 70s, there were no possibility to build 42-ton mirror from another sort of glass. So this ordinary glass, and we found the polished layer is strongly degraded. We have because it was recoated many times, almost 20 times. When I became a director, I found it 20 times recoated. I don't know why, but there was a fashion to recoat it each summer, and the layer was slightly destroyed. So we had to replace the mirror. But we have two. First of them is now the telescope from 1979, and second one as a spare mirror. And we decided to change the mirror, but the first idea was to use the existing blank of 8-meter mirror, not 6, but 8-meter mirror, which exists up to now in Germany, a company Short, because the company which built the blanks for VLT telescopes. The idea was to remove the 6-meter mirror to put inside the flexible active mirror of the larger diameter, so the area will increase. The total it will be 2 times larger mirror, because 8 meters to 6 meters. And of course the tube will be shorter, almost half factor of 2. Just the problem was how to move these balconies. But of course the problem was the budget of the country. And the Academy of Science refused. By the way, the CCCP, it's USSR in Russian. And we still keep this sign on the telescope because it was built during the USSR time. So we could not prove that we need to replace the mirror, and therefore the idea was to put, this is, by the way, the blank in Germany, Schott company. We studied it in details. And we decided to replace this mirror now, and to put a new one, repolished under the factory. So this is transportation of the mirror to the company. Well, I come back again to this camera. So now this process is not finished. We sent the mirror in 2007, but because of the economic crisis due to Americans all over the world, we have no money to finish the repolishing of the first spare mirror. So we still are waiting to finish it. And the company does not give us the mirror because they pay us first and then return it. Yeah. So the speckle history started with these guys. Maybe you know this guy. Who is this? This is Antoine Labeyrie. You know this? Antoine Labeyrie. It's in 77. I made this photo. This Laurent Quéclin, also French, and this Renaufoy. From these guys, Renaufoy is still active. We are still working. It's 1 year ago. So almost no change. Almost no change. And this is the same detector as my colleagues just explained, EMCCD, the same company, the same, okay. So we are doing spectroscopy. This is example of one, I don't know which one, from Hipparchus list. The field is 4 by 4 arc seconds, and this is some sort of binary. And what are the targets? The targets are very different. We have many different programs using speckle. First of all, nearby low mass stars, as already been explained today, young intermediate mass multiples in star-forming regions, massive stars like Theta 1, Orion C, symbiotic stars, binaries with magnetic components, multiple systems with eclipsing population 2, and different peculiar stars. And I will give you some examples of what we are doing in a speckled field with a 6-meter telescope. First, when we discovered it in 10 years ago. So we discovered it first, we suppose this is something similar to Orion trapezium. So we are happy because this could be an unstable system. But unfortunately later we found that simply like a project because this component is slightly farther away. By the way, this is a comparison with adaptive optics independently. So we're not correlated observations. They resolve this star Martin in the same time, Keck, H band. You see absolutely the same results. I always like to say that adaptive optics is the same as speckle, but adaptive optics use real-time mechanical compensations, while speckle use more sophisticated processing as a post-processing. So we have the same result in principle, and speckle can give you higher resolution. So this is advantage, as today Elliot told about the sub-diffraction resolution. This is standard if you have signal-to-noise ratio high enough. Plus, speckle is able to work in the visible, while infrared still is problematic because of the many reasons. So this is example of another example of multiple brown dwarf system. It's a triple brown dwarf, resolved also with a 6-meter telescope, then later with Keck telescope confirmed. This is a binary dwarf here, and this is a third companion here. But we established the orbit, about 1 AU orbit, and period 3.5 years. At first estimate, the mass sum was given here. Then we know today that the mass is about 50 Jupiters for each component. It's another example where I will not spend too much, just typical star. So this is, I think, the best, not I think, everything the best, I think the best. This is mass luminosity ratio for normal stars. This was published by Torres and Anderson a few years ago. So the masses of these stars are known with an accuracy better than 2 or 3%. So this is the best relation. But you see that this lower part, which is below the solar mass, is not very well known. Or there are only GG, Gemini, and YY, I forgot, Draconis, the components. All other stars are not known with such a good accuracy. So we have to work hard to improve this lower part of the mass luminosity relation. And these are examples of new binaries discovered. This is nothing important, but to give you an impression how it works. So the targets are multiple stars in different OB associations. For example, this is Cassiopeia Taurus associations as a new binary with a distance about 100 milliseconds. And we use the power spectrum to get the parameters of the system. So from the orientation of the lines, we have the orientation of the binary. From the contrast of the fringes, we have the magnitude difference. And if we need an image of a star, so we use of course, phase reconstruction using bispectrum Weigel's method. But this is used only in case if you need to publish some nice pictures. Typically, all the information is here. And this is an example of the table, which is the list of new binaries discovered in these Cassiopeia-Taurus associations, distances, and different parameters. Another example is eclipsing. So we have many eclipsing variable stars in our lists. For example, this is V3789, in Cepheus. An example of that we see in eclipsing binary the third component, very close. You see the diffraction limit of the telescope is here shown. So the fringes show that the binary is 20 milliseconds apart. Another eclipsing binary 649. This is quadruple system. One system of fringes is like that. Second fringes is like that. So it means a triple system with a distance is 16 and 176 milliarcseconds. Interesting pair, CH Cygni. So we observe it regularly, and there was only, thank you, always the single star, no result. Suddenly, when in 2007 we reprocessed the data which were taken in 3 years before, we found that we can see the white dwarf in the system. So this is a binary, the red giant, evolved star, and white dwarf here. Because of the accretion on the surface of the white dwarf, sometimes, some periods, we can see the secondary companion here. Unfortunately, later we observed every semester, but no result, because it was the phase when it was bright enough to be resolved using speckle interferometry, and the magnitude difference was about, not very large, by the way. See 2 magnitude difference in the visible. So it's a good example for cooperation, because you never know when it will explode again. The example of the low mass and low metallicity systems, the name of the system is given here, and this is a metallicity, so 100 times less metals in chemistry than for our sun. And what is interesting for this pair, we have observed a lot of them, that it's quadruple system. One of the components is more or less speckled. You see, where is it? The distance I don't see here. So it's here. It's large, almost 1 arcsecond separation between the components. But what's in it, because this system made at least between 20 to 30 revolution crossing the plane of the galaxy, and it still contains as a quadruple system, so it still exists. So it's interesting that the system was not broken by the gravitational forces during the revolutions in our galaxy. So the conclusion is that some systems exist which are very old, 10 billion years, and still can be kept as a single system. Yeah. So I don't think there are many, because we have a strong group on magnetic field research. So we studying the binaries in with magnetic components. The primary star is always a brighter one, and it's a magnetic star. Because of some reason, secondary is not magnetic. And we study this with speckles. So it's very strange if the star is binary and they are formed from the same material. So if it is a relic origin of the magnetic field, why one star has a magnetic field, a second one no, second one not? Probably the answer is very simple. This is a result of evolution, and the brighter star, which is more massive, develops some way dynamo mechanism of the magnetic field in the star. And this is just for the conclusion, one of the peculiar stars, 41 Draconis, very well-known star. This is accelerated by a factor of, I forgot, few millions motion of the star on the orbit. And this is a quadruple system, extremely interesting, because during the passage through the periastrum, this is a star with the highest eccentricity among all known stars. You see the eccentricity of the orbit here. So when they are slightly evolved, and when these stars pass each other, they are almost touching. So they are pseudo. What is in English for pseudo? Pseudo synchronized systems. So they are always turning to each other the same size when they pass here the periastrum. very interesting system because at that time in spectrum you see very strange effects. And speckle orbit has to be improved because there is also a second pair in the system, and we need a lot of constellation. Thank you very much. I will stop its motion because.
I think a couple of questions.
Yeah, questions.
So for the quadruple system that you said had 30 crossings of the disk, right?
Yeah, something like that, between 20 to 30.
So is the orbital plane of that system known, or is there any orbital information for the components of that system?
We estimated just from the simple ideas. General motion of this system is known because it is a high probable motion system, so know how it moves, and we can estimate how many revolutions it made already.
Okay, yeah, I was just curious to know if the orbital plane might be aligned in such a way.
Yeah, that's very complicated because they slow movers.
Right.
Yeah, I don't know that. I cannot answer.
Thanks.
Yeah, Bobby.
For the double that you said the primary was magnetic and the secondary was not, do you have conclusive data that shows that one is in fact not magnetic?
Yes, from the spectrum we always see that because of Zeeman effect in the spectrum, we see that this one of the stars shows the Zeeman effect, second one not. But in the lists of AP stars, which are probably some of them are magnetic, yeah. In this list, which is over 300 stars, all of them, only one component has magnetic properties, while second is not. So it's very strange.
Yes, right.
That the secondary, which is fainter, never shows any fields, any magnetic fields, on what we know.